他是这个意大利都灵大学毕业啊，博士毕业。毕业之后呢，他拿到了这个全球的这个玛丽居里学者，那么是在基于是 Global 的 Global 是跟 UCL 就是伦敦大学学院和这个 MIT 一起。那么它的主要研究方向是做这种结构的优化设计。那么具体呢，就是主要是做既有的钢结构的这种优化设计，以及重利用等等。那么我就多的话我就不说了。然后呢，我们接下来把时间交给 Dr. Raffaele Cucuzza. Okay, so we can start.
Okay. First of all, I'm so sorry for this late. A taxi driver bring me at the east gates and not north gates, so we have some problems, some troubles with Kang. Yeah, here this is just a brief introduction. Of course, thanks a lot to Professor Kangao for this nice introduction. I will show you some preliminary result of my research, and 2-3 days. There are some. Okay, maybe someone could be on mute. Okay, that's great. Okay, this is my voice that is recording somewhere. Maybe we can do like this. Can you hear me? Okay. No. I stopped the audio. There's something that when I speak, wait.
Why is just recording your voice? It's here. It is.
I am not hear you.
Can you hear me? Can you hear
Yeah.
me?
Now it is okay.
Okay. I hope that now it works. I don't know. We can try. Wait. We can do like this and like this. Okay. We can try again. Can you hear me by remote?
Yes.
Okay, great. So I'm so sorry again. I will show you some preliminary results on my research. 2 days ago, I was in Japan to the World Conference of Structural Multidisciplinary Optimization. I know that Professor Kangao knows very well this conference, and during that conference, I delivered a keynote speech on a multi-criteria decision-making tool for the optimal design of building made by reusing steel. So, guys, I think that the first thing that we have to fix during this speech is what is the real topic of my presentation. The real topic of my presentation is reusing steel. Reusing steel. There is some of you can have the hands up, can have heard about reusing steel. There is some of you that know about reusing steel. Or this is the first time. Reusing steel? Reusing steel? No? So this is the first time that you heard because it is a really hot topic, okay? Maybe you have heard about recycling steel or recycling concrete, right? Great. But in this case, we are speaking about reusing. So first of all, we have to distinguish what is the main difference, the huge difference between recycling steel and reusing steel. So this is the table of contents of this presentation. At first, I know that there is some of you that work with Professor Kangao, and you work in the field of metamaterials, image detection, and so on. So the first real question is steel the material of the future in the construction center? So we are researchers, we are scientists, okay? So we have to wondering if conduct research in the field of steel is quite useful or not, okay? So I will show you some statistics, especially in China. I have some statistics and some data that my colleague, my friend shared with me about the use of steel in China and over all the world. The second is the big difference between reusing and recycling. The main topic of my speech is not recycling concrete or recycling steel. My main focus is reusing steel, and we will see how to reuse steel. And what do we know about reusing steel? So what is the current knowledge about reusing steel? Because it is a very new topic. So I would like to share with you what I find during my lecture review, during my state of the art that I conducted until now. And then I will show the REACT projects. This is a Marie-Curie Fellow. I will give you more detail about it. The Marie-Curie that was won with MIT and other partners, USA partners. I will show you in detail much better later. And finally, there is, I think, one of the most important things. I have submitted a paper in Nature Communication about that. A new reusing steel supply chain. So at the end of this speech, you will know what I mean with the reusing steel and why we need a new supply chain on reusing steel. So this is some statistics I provide. Of course, after this presentation, I will give all this presentation to Professor Kangao, and he would like to share all this information with all of you. And here is reported all the references, so you can find all the references and you can find the same data. And these guys are the world crude steel production from 1950, so after World War II, up to 2021. So it is, I think the most upgraded statistics that we have in Europe. If you take a look here, of course, it is quite evident that there is an increase of steel, of course, in spite or despite to the concrete, especially here in 2005, 2010, or 2005 and 2000, we have a huge and steepest increase of the steel. So, if I take a look to the last year, you can see that the increase of the steel is a little bit low, is more soft, okay? So the real increase of steel is more or less during this era, in this period, okay? In which we were, in 2000, there were a lot of technologies, especially these are the world crude steel production, not in civil engineering, but in all the sector, in all the engineering sector, okay? So especially in 2000, there were a huge pressing needs of technologies and especially different type of technologies. So the increase of steel was quite evident. So this is other statistics that I found. This is, a very well-known association. So these statistics, believe me, are quite credible. And if you take a look, I'm ranking here what are the top 20 steel producing countries up to 2020. Of course, the first ranking is of China, of course. China here, this is the tons, the million tons produced by China, okay, in all the sectors, not only in civil engineering. At the second place, we have India, and the third place, we have Japan. Especially why Japan? Japan, if this is China, Japan is very, very little. Why Japan produces a lot of steel? Because, of course, it is a seismic area, and especially in the civil engineering field, but not only. Also, Japan is quite famous for a lot of car company, automotive. So they produce a lot of steel for that. So this is the ranking. But if you take a look here, I reported here also a picture that can show you that if, of course, the statistics have to be upgraded, But in the next year, if you take a look to this link and if you surf on the internet, you can find that these data are changing, especially the amount of steel that is produced is decreasing, okay? So what it means? It means that the society, the world society, is pushing on environmental circularity. Circularity, what that means? I have to use this plant, okay, or I have to use my pen, and after that my pen is died, I can use again for another product, okay? So I need something like that in order to improve and increase the sustainability of this world, okay? And I know Professor Kangao told me several times that also in China there is some governmental policy that are pushing on the sustainable construction. So this data will change. The first place of China will remain the first place, but the million tons of steel will decrease, especially in the USA. USA, you know, I'm sure that some of you is surprised and say, "Oh my God, USA is just 4 ranking in this. It is not in the top 3." Because in USA, there is a huge production of concrete, So this is some ranking that I hope that Professor Kangao will ask me next year, of course, within this project. And I will show you the updated statistics about that. So guys, if you remember the table of contents, I would like to share with you some data. But now it is the time to make a clear distinction between recycling and reusing. Especially what it means recycling. What is the definition of recycling? Recycling, especially for structural steel work. So we are speaking about steel for civil construction sector. Recycling is the current method of turning waste, scrap metal, into a new product. So I have, for example, a steel beams. I can put in the factory. In the factory, I melt, and I can use this scrap metal, scrap waste, in order to produce a new steel beam, or I don't know, the shell of car or something like that. So recycling means that there is a circularity, okay. But take a look. This is the most important thing. If you don't understand this, I am sure that you will not, understand what is the result of my project. This is the steps that you have to follow if you want to make recycling. Especially, you start with collecting. Of course, I have to demolish the building. I have to collect the beams. Okay, this is the first stage. Then there is the shredding. Okay, melting and refining. I have to melt. Okay, I have to take the existing steel and I have to melt again. I have to refine, I have to process. And finally, there is the casting rolling. Okay, I want a beam with a steel beam with this geometry, with 23 millimeters of flange, with the web of 50 millimeters thickness, and so on. So I want this specific type of steel beams. This is the process, guys. Please take a look to this one, melting. The melting is the quite most expensive process from the CO2 point of view, CO2 emission, and also from energy. I need a lot of energy in order to process the melting for steel. If you take a look to reusing, okay, reusing means extending the service life of structural functional parts with little or no reprocessing. So I repeat again, it is not recycling. I can take the waste, I produce the waste, and I create a new product. What I mean here is that extending the service life. So it means that if I have a steel beams, I will take the steel beams. Of course, I will give you more detail later. But I take these steel beams, I check if the steel beams is damaged or not, and then I put the same steel beams in another building. What is the big difference? If you look here, There is just three steps. Of course, this is just a simplification, a simplified way to see, of course, the process. There is collecting. I have to collect the steel because I cannot demolish. I have to deconstruct. I have to put the steel. I cannot go to the group and destroy it and demolish my building. I have to take the beam very carefully. I have to stock in my factory and so on. Then I have to test. Okay, I have an existing building, an existing beam. Okay, but this beam is damaged or not? I can use this beam for another building. And finally, I can just, make some minor alteration, minor modification. Okay, this beam is one meter length. I want a beam, it is 5 meter length. I want a beam that is 3 meters length. Okay, I will cut. This is the only thing that I can do. I can modify, but the geometry is always the same. So what are the main benefits, advantages, and disadvantages of this steel? As I said before, in the recycling steel, okay, it is the same also for recycling of concrete. It's always the same. So this is quite useful for both the processes. Clear and well consolidated supply chain. You know what is the supply chain? The supply chain is more or less, okay, Professor Kangao sold me the steel. I buy the steel, and we are two partners of the supply chain. Then I will give to you, and you will process the beams, okay? Then there will be another guy that will say, this is the supply chain, okay? All the stakeholders that are involved in the supply, this chain. So we know how to make recycling. In the industry, in the factory, especially in the construction field, they know how to make, how to establish recycling. They know very well because we start to recycle steel since 20 years ago. Second of all, high accuracy. When I'm recycling a piece, I know exactly what is the expected performance. Okay, I have a beam. I'm recycling this beam. At the end of the process, I have a beam that I know what is the maximum strength. The maximum strain, I know everything. I'm sure that that beam will work as I want. Consolidate the level of knowledge on steel from scraps. The scraps are waste. So I know very well, I am the boss of my factory. I know very well how to convert scrap waste in new products, in new steel. And finally, energy demanding, but what is the real problem? Energy demanding and partially circular process. This is the problem. They are really energy consumption. Okay, they produce a lot of CO2 emission. Here we have some benefits, but we have also some disadvantages. First of all, what is, guys, the big difference between this process and this process? Just on your opinion, what is the big difference between this process and this process? The big difference is that in the reusing steel, I have not melting. So in the reusing steel, I delete and remove what is the most consumption, the most energy demanding phase. So no remelted process. That's good. High energy and CO2 saving rate and saving a lot of CO2. Of course, if you remember here, I have to certify. So I have a beam. I have to certify if this beam that was working in another building, it is damaged or not. I can use again for another building. I have to specify. There are some protocols. There are the passport. You know the passport. I'm traveling a lot during this period, and I have my passport, name, my surname. It is the same for the steel. I have one passport for that specific type of beams in Middle East. Okay, this is an I-shaped beam with 5 meters length, with the thickness like this, and so on. Okay, I have other information. This is mandatory for the factory. Problem. This is quite generic. General. I will show you much better later. Cultural, technical, and supply chain parts. We have a lot of problems with that. So this is why I'm here to speak about steel, reusing steel. So, at the end of the day, the construction sector, this is other statistics. The construction sector accounts for 25 40% of the total CO2 emission global. Oh, just the civil construction sector, guys. There is some of you that, of course, all of you are civil engineering students, right? Right, guys? So in the future, all of you will produce at least the 25-40% of the total CO2 emission global. Okay? Just the construction sector. And please, when there is someone that say the most CO2 emission sector is the automotive or transportation system, it is not true. The most CO2 emission sector is ours, the civil construction sector. It's not automotive. When there is someone that says this, they say there are bullshit. It's not true. It's not true. The second aspect is that steel is a circular material, recycling, circular material. Nowadays, the 85% of steel is already recycled. So there is a lot of company that already recycle steel. There is no company that produces new steel. They just take the waste and try to recycle it. Studies, especially there are some papers that are published in this field, it's possible to reach the 50% of reusing threshold. So I can take a building, an existing building, the building of my grandfather, okay, old building. I can take the 50% of the existing beams and I can put in the new building. Okay, is it possible? You can do it. So at the end of the day, these are the amounts of kilogram of CO2 emission per tons that are produced for reusing structural steelwork and new structural steelwork. The new structural steelwork CO2 carbon embodied carbon emission is 3 times more than 3 times than the reusing structural steelwork. So, there is no match. There is no match. We have just 50 kilograms CO2 emission. So the reusing steel is not comparable with the new structural steelwork. So why we don't use reusing steel if this is so convenient? This is the reason, guys. Of course, I come from Italy, as Professor Kangal told you before. And here I reported this is some references from which I take this information. And these are Europe, This is Italy, this is my hometown, Sicily. And, just in Europe, you can see that UK is the most virtuous, the most, the country with the highest level of reusing steel, okay? UK works a lot in the field of reusing steel. All my research is mainly established in UK, not in USA, okay? And here, for light steel means non-structural elements, steel for non-structural element, the using rate is 5%. So over all the steel production, just the 3% of light steel is for reusing, and only the 7% of heavy steel, so structural parts of the building, can be reused. Italy, France, Germany, Spain, all of that are negligible rate of reusing steel. It is 0.003%. It is negligible. Okay. So just in Europe, only UK is, contribute to the feeling of reusing. So guys, this is one, of course, all of you know, what is the name of this guy? Sorry? What is the name? Einstein, of course. And this is one of the questions that I like a lot, because we are speaking about reusing steel. We have seen that reusing steel is quite convenient. I can reduce the CO2 emission. So there is one question. If the reusing steel is so convenient, why we don't use it? And there is one famous sentence that Einstein, remember, is wondering at the time, a question that sometimes drives me hazy. What is the question? Am I or are the other crazy? I am the crazy guy that thinks that reusing steel will be useful, or are the other. Okay? So I hope, of course, that I will not be the crazy guy. So there is some reasons why reusing steel is not used nowadays. There is some reasons why just UK produce reusing steel. And here I reported two types of barriers to reusing steel. Real and perceived. Perceived means virtual, okay? Are virtual. Barriers to steel reuse. In fact, here there is a guy with a real wall, and this is a guy with a virtual wall, okay? This is what sometimes it happens that, I don't know, you are students, so maybe you attend the course of Professor Kangao. Professor Kangao, of course, there is the exam. You have the exam, right? And you have to receive a mark, and sometimes say, oh, I cannot pass this exam. This is too much little for me. This is a perceived barrier, okay? So here, the first real problem, concrete problem, that we have in the field of reusing is that limitation at the design stage. We have a huge limitation, guys. Imagine to have beams, okay, of the existing building. So this is my beam. I put this beam, this is a columns. I take these beams from these columns, and this columns is 5 meters, maybe 5 meters length. I have to use these beams exactly just as it is. I have to use these columns exactly with the same length, with the same cross section and so on in other building. It's a lot of limitation that. No? I agree with me. So, especially, Professor Kangao work, and all of you work in the field of topology optimization, right? Okay? Topology optimization, or I work in the field of structural optimization. Okay? I'm working on size, shape, and sometimes also topology optimization. Since the beginning of this field, all the scientists try to optimize a building for what, guys? If you optimize a building, what do you want to obtain? What do you want to minimize? For example, the weight. I want to minimize the weight, for example. Okay? The problem here is that if I have to take this column with this geometry from the existing building, and I have to put in a new building, how I can optimize? I have already my section. I can just use my section. I can just use that section as it is. I cannot optimize. I cannot produce something that is more slender, that is thin. I cannot do that. The second one is how to guarantee safety. I take this column, but I don't know if this column is straight or not. I don't know. I have to put this column in a new building and be sure that this column is good. Time-consuming the construction, respect the demolition. Guys, demolition right here, I destroy everything. Oh, I put all this building collapse. 5 minutes. I will put some bomb. Okay, I will put some glue and destroy everything. If I want to make reusing, I am obliged to take this very carefully. Put here, certify, test, and so on. So I have to be very careful, and this is really time-consuming. And time-consuming certification process. I have to verify, I have to test. What happened in the previous life? To this column, what happened to the previous life? It was damaged or not? These are the real barriers. But there are some barriers of the mind. There are the barriers, the interior barriers. The first barriers is lack of reuse markets and supply chain. You remember the example that I gave you before? I am the guy that had the steel, Professor Kangao has the steel. Professor Kangao sold me the steel. For me, I buy the steel. This is the supply chain. The problem is that Professor Kangal solved recycling steel. He has not reusing steel. So we have not stakeholders right now in our century that work in the field of reusing supply chain. So they need to establish a new reusing steel supply chain. And the second of all, reuse by perceived as second-hand. Guys, there is some of you that have Apple device, and now there is some of you that have. Guys, you have Apple. This is Apple. Who else? I know that all of you have Apple. It's a lot of. I have Huawei. I love Huawei. I love Huawei. I don't like Apple. But do you remember that time? Do you remember that time in which Steve Jobs is starting to speak about reconditioned Apple? You know, Apple that are made by whole pieces, whole parts of previous Apple. So I have my device. This is Huawei. I have my device. Okay, this is very old. Okay. I want to buy a new Apple. Okay, I will take some parts of this. I will give to Apple, and the Apple give you something that is more or less the same of a new Apple. Okay. At the beginning, they were really preoccupied. The people say, okay, I'm giving you a device, a reconditioned device, but this is not new. This is a second hand. This is something that is not really new. And the people say, oh, I don't want this. I don't want this. This is something that maybe doesn't work. This is something that maybe has some problems. I want something that is new. So the problem of reusing is that if I take an existing column and I put in a new building, the people say, I don't want a building made by a second-hand part. I want something that is new. I want a new Apple. I want the reconditioned Apple. Okay, guys, do you understand what I mean? So this is a problem of our mind. Okay? I want new clothes. I don't want the clothes of my friend here. I want my new clothes. I want to go to the shopping center, especially the ladies. I want to go to the shopping center. I want to buy my new t-shirt because it is new. And new means that it's better. Sometimes new doesn't mean that it's better. There is some cases in which new could be worse, much worse than reused. So these guys are, now we can approach the real part of my presentation, the core of my presentation. So if you remember the name of my Marie-Curie Fellow is React. React means, you know, if I push this like this, I have a reaction. Okay. So React means try to change that thing. Try to change the future. React is an acronym that means reusing steel for emission reduction through AI-driven cutting stock tool. So the idea is to develop a tool that is embedded in, you know, SAP 2000 guy. SAP 2000 is well-known, famous software. So a tool that is able to be plugged in the SAP 2000, okay? And I am a designer, not a scientist, I am a designer. I want to go to my SAP 2000, I am building, okay. I am a building and I want to make a choice. I want to design a building with new steel, or I want to design a building with reused steel. My tool, what we are working on, is a tool that is able to do this. Deliver an automatic tool. I will show how it works, because I'm working on it. And that is based on cutting stock. Cutting stock. I have to cut the steel members. I will show you better. The partners that are involved is MIT, that is the main partners, and then here I have listed also other partners that will participate to these projects. First of all, UCL. I hope that Professor Kangao knows that now I'm moving. UCL is one of the main partners, and probably I will join to this university in the future. So UCL is one of the top universities in the world. This is the first, especially the Bartlett School of Sustainable Construction is the first in the world for sustainable construction. So green eco design, green transition. And in USA, I will spend 6 months in Northeastern University with Professor Ajar. Professor Benjamin Ajar is one of the most important scientists in the field of steel structure. And here, I reported some association. This is the American Institute of Steel Construction. This is an association. Of course, guys, I need data. I need steel data in order to make this tool. And this is the British Construction Steelwork Association, British. So it's the same of this, but in the UK. And this one is a Festos Hub. If you search on the internet, you will find a lot of information of a Festos Hub. The main partner of a Festos Hub is one of my best friends, is Professor Samaridis. He's a Greek guy that's, he's a professor in UK. And he invented this app. It is a center, a research center, but in which you can make also money. It's a company, a private company, in which they develop tool. They work with SAP 2000, with Tekla. They develop tool, AI-driven, okay, for the design of building, for the design of bridge, for the design of structure and infrastructures generally. So, if you take a look at this picture, I hope that you will like it. We have the main steps of my projects. We can start with the deconstruction. You can take a look at the upper of this slide. You have this building that is deconstructed. First of all, in the work village one, we have to establish a database. So I will take this column, that bits, that columns, that columns, that bits. I have to collect this data and I have to create a database with all the steel. In the work page 2, I have to formulate the optimization model. And we have objective functions, design variables, and constraints. I have to use type, shape, and topology optimization. I will show how. Then there is the core, the real core of the project. That is that one on the screen here. This is the core of the project. If you take a zoom here, you can find that we have a Pareto front. Do you know what is the Pareto front? Of course, yes. Pareto front, because you work with Professor Kangao. Professor Kangao know very well what is Pareto front. So, if you take a look here, we have x-axis and y-axis. X-axis, new steel. Y-axis is reused steel. So, solution B is a solution that is shiny. This solution is new steel. This is building made by new steel. Here, new steel. What it means, new steels? We have three quantities. First of all, CO2 emissions. Second of all, dollars, money. What is the cost of this project? And this has the weight, kilograms. The weight of my structure. So, if I use new steel, I have a very slender steel, because I can optimize structure. If I have a new steel, I can say to my friend Professor Kangao that sell me the steel. Professor, I want 3 beams like this, 2 beams like this, because I design in an optimal way my building. The problem is that we have a very increase on the carbon emission. So my idea is try to reduce this embodied carbon. So we can go in solution A. Solution A is the opposite solution. I want a building that is made by only reusing steel. If you take a look here, we have CO2 emission that is very low, because I can, of course, optimize the embodied carbon. The money that I need for the construction maybe is lower, because I'm not obliged to melt it again. The problem is that the weight of the building is increased, because I cannot ask to my friend Professor Kangao, Professor, I want 3 beams like this, 2 beams like this. No, Professor Kangao told me, Raffaele, I have just 1 beams like this, 1 beams like this, 1 beams like this, 1 columns like this. I have a limited stock, so I have to use that for my building. And this means that the weight increases. So what is the best solution? The best solution is a trade-off, is a balance between solution A and solution B. If you take a look here, there is new elements, and here the colored one is reused element. The balance. What is the balance? This is a very complex problem. Imagine that you have this building. This building is a very huge building. It is a building that is perfect for my tool. We have a lot of columns, a lot of beams. We have a lot of elements, structural elements. So there is a huge complexity that we have to manage. We cannot do by ourselves. My father is a designer, cannot design a building just, okay, I have this stock, I have to maximize the reagent rate. It's so difficult. So I will use the casting stock problem tool. I will show you better what I mean. So, this is the basic idea. And of course, this is a Pareto front, because I want to take what is the optimal solution. I have different optimal solution. I want to take the balanced optimal solution. Of course, if you take a look here in the previous slide, here, of course, I reported here the Marie-Curie action. This is, of course, the name of the fellow. Professor Kangao won my same fellowship. It is one of the most important acknowledgements in the field of research for research fellow like me. In a work-rated form, I will validate my tool in a benchmark test and real-world structure. I put the felt hour just to give an idea that I will test on real structures. We have real building. And finally, we will implement and we will deliver this tool openly to all of you that have the license of SAP 2000. So you can enter SAP 2000 and you can find my tool there. So now, you remember that here in this slide, I reported here active stock problem 2. Active stock, the still stock 2. What is this casting problem tool? These are casting stock problem tool. This is a mathematical problem. It is a combinatorial problem. It was solved by Kantorovich, a Russian guy, in 1960. So it is a very old problem. It is a very complex problem. And how it works? We have a truss beam. This is a very common truss beam. This is our always truss beam. So we have 4 different types of beams. We have green beams with specific section. A is section. Specific length. Okay, the length. And we have also member blue, member red, member yellow. Each member has specific section, specific length. Okay? Now, here, so this is the truss that I want to build. This is the truss of the designer. The designer comes to my office and says, I want a truss beam with these elements, with this section, with this length. Okay. We can move to the factory. Professor Kangao has the factory. He has to produce the steel that I want. And Professor Kangao told me, I cannot produce these steel elements. I produce a steel elements with the same cross section, but the length is standard. In the factory, the length of the steel is 12 meters, maximum 15 meters. You know why? Because in the civil construction sector, if you make a beams in the factory more than 15 meters, you have problems during the transportation phase. No? You have to use ships, you have to use not car, but you have to use flights or something like that. So I have standard elements. I have elements with A1 section, but it is the length of the beads. Beads in English means the standard pieces. So the length of beads is always the same, always the same. What it changed is the cross section, guys. So the problem is that I have these elements, I have to cut these elements here in order to obtain this one. So I start from this and I cut. You can see the cutting here. I cut like this, and in this way, if I cut like this, from this, I can obtain 1, 2, 3, 4. This is wasting. Okay? 4. 1, 2, 3, 4. So from these beams, I obtain 4 elements. Okay, that is of my beam. This is how the cutting store problem works. So, as I said before, what is the novelty of this approach? We have a paradigm shift. In my field, but also the field of Professor Kangao, the field of research in which you work, all of us, the objective function is always minimum weight. This is a problem. In the company, they don't care if the structure is slender or is fat. They don't care. They just care how much money I have to spend to buy steel. This is the real difference. So, my mentor, Professor Marano, that is one of the big names in the field of structural optimization. I remember when I started my PhD, 6 years ago, something like that, 7 years ago. And I remember that Professor Marano told me, okay, I am an expert of structural optimization. We can minimize the weight of the building, the energy, the embodied energy of the building, the embodied carbon of the building. We can minimize everything by changing the size, the shape, the topology of the building. Okay? In order to obtain the minimum weights, for example. I remember that after 5 years, 6 years that I worked on new algorithm for structural optimization and so on, he told me, Raffaele, after 40 years that I work in this field, I realized speaking with the companies, because what I like to the research of Professor Kangao is that, and what we are quite lucky to work with him, because Professor Kangao is not like a scientist. In China, he worked a lot with companies. You know what is the real problem. Because, guys, remember that we are researchers, we are scientists, but we are also engineers. We are engineers. We have to solve real problems. We are not mathematics. We are not physics. We are engineers. So we have to solve real problems. So the idea is not the traditional approach of the minimum structural weight, but the minimum waste. You remember, guy, in the previous slide, if I cut like this is waste. I cannot use this part here. I cannot use. I cut, I have 1, 2, 3, 4. 1, 2, 3, 4. I don't need more. So this is a waste. But the factory pay this waste. The factory pay. When they buy, they don't buy 1, 2, 3, 4. They buy this one. So they buy all the amount of steel. So here there is, slender structures do not lead to minimum cost, what I said before. We have to think about minimum waste from the factory. So structural optimization through cutting stone problem. We have to implement the cutting stone problem in the structural optimization. And this is the preliminary design, some preliminary results, of my research. You can find more detail in my papers. Here, if you take a look, we have a truss beam. And this is a Warren truss beam. And we have different approach. This is the traditional approach. I want to minimize the weight. This is the minimum waste. I want to minimize the waste, the dashed area. So I have this truss beam. I want to build this truss beam. This truss beam and this truss beam are the same types. But I have two philosophies, two strategies that are different. One strategy is the minimum weight, and the other strategy is the cutting stone problem embedded in structural optimization. So what happened here? Here we have, if you take a look, we have section A, 1, 2, 3, and we have to, these are the bars, we have to assign all these elements here, okay? So I perform a topology shape inside the optimization. So this weight is increased the height, I change the size, I change the shape, I play with the coordinates of the nodes in order to maximize what? Here, I want to minimize the weight. Here, I want to minimize the waste of the structure. If you take a look here, I need to, with the minimum weight approach, to build this truss beam, I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 bars. If I use the minimum waste, I have 1, 2, 3, 4, 5, 6, 7, just 7 bars. So I have reduced a lot the amount of steel that I need. Of course, this piece is slender than these beams. This is heavier. This beams is heavier than this because I have, optimized the waste. If you take a look, this is the waste. If you take a look at the top part, the waste is reduced. I want to minimize the waste. I want to maximize the performance, the use of my stock. If Professor Kangao has 1, 2, 3, 4, 5, 6, 7 elements, I want to use all the 7 elements as much as possible. So this is a first example. Then we move to another example here. This is more complex. It is a geodesic dome. It is a 3-dimensional. And if you take a look here, more or less we have the same results. Minimum weight from the factory, cutting stone problem, and minimum structural weight, additional approach, minimum weight. If you take a look here, and if you compare the wasted area here and here, you can see that these methods bring to a slender structure, but the waste is uncomparable. So, and we are approaching the end of this presentation. If you take a look here, you can see that, remember one of the perceived barrier. The problem is that Professor Kangao has just recycling steel. He has not reused steel. And there is few companies that work in the field of reusing steel. So the problems is that we have to establish a new supply chain. So how my research could really impact the field of reusing steel? This is my question. I have to establish a win-to-win approach, and I called this new supply chain Markovian chain. You know Markov? Markov is a famous scientist that You know, it was a mathematician, and he, or a physicist, I don't remember, and he basically he says in a chain, the information at the step I is important for the step I plus 1. So the information that I have at the step before is useful for the step after. And in my supply chain, I want to establish exactly the same. I start with my tool. Okay, so at the end of these 3 years, I will deliver my tool in SAP 2000. Then, first of all, and I am exactly in this stage, I have to establish the interaction between no-profit association and companies. I have to convince the people that to share data, because there is a lot of American association, there is a lot of company that know how much steel they have. There are some construction company that they construct the building, so they have this data, and I would like to get access to this data. Then I have to collect the data and storage. I have to establish a database with all this data. Once I develop my tool, I will implement to SAP 2000, and so the software house will be contacted. I have a contact with the software house CSI in USA, that is, of course, partner of this project. So, guys, this is the most important thing. Why the company should share the data of steel? We know, Professor Kangao knows very well, that the company in any field, they are really jealous of the data. They don't want to share the data. So why the company should share the data? And the answer is quite simple. If Professor Kangao shared the data with me, he told me, Raffaele, I have a stocks of 2 tons of these beams. Okay, I will collect this data, I will put in SAP 2000, and he that will use this, he is a designer, he wants to design a new building, okay? When he will ask to SAP 2000, there is a button, cutting stone problem by Cucuzza. He will click this button, and immediately the SAP 2000 will give you the final design of the building with the optimization of the stock. So it means that if Professor Kangao has a stock of steel that can match with the design of my designer, Professor Kangao will sell easier the stock. So there is a benefit for who shares the data. If you share the data, your data will be used by the designer in SAP 2000. So in SAP 2000, I have real database, because people that share the database are real people with real stock of steel. And when the real designer goes through the tool and he design the building, he will design a building with a real stock. And when the designer says, okay, I like this design, what is the stock? The stock is the stock of Professor Kangao in Southeast University. Okay, I will call Professor Kangao, I will contact him, and I want to buy this stock. This is, guys, a business chain, okay, in which the software house wins. Why win? Because SAP 2000 has a new tool that is catchy. The companies win because the companies, of course, of steel can sell the steel, and of course win the world because we are pushing on the green transition of the construction sector. These guys are just some picture of my last work. There is one picture with Professor Kangao which we tried the metamaterials, some experience in Southeast with Professor Marano and Professor Domaneschi, some experience he has in Fuzhou. Here there are some pictures in Nanjing, and this is my class in Guangzhou in School University. This is my classes here. This is Professor Briseghella. professor that is the dean of the department at the Fuzhou University, Fuzhou University close to Taiwan. And these are Professor Stergios Mitoulis. It is one of the biggest, name in the field of sustainable structures. And here I was in Birmingham and UCL, and I spent some time, two periods, visiting period there. And thanks a lot for your attention. And if there are some questions, please ask me.
Okay, thank you so much, Dr. Raffaele Cucuzza. A very fantastic talk, a very interesting topic. And so, 我简单来介绍一下，我的个人理解啊，大概我在20年前的时候，在读大概15到20年前，在读本科的时候，那个时候呢，我们国内刚刚开始做所谓的这种再生混凝土，就是混凝土的再生利用。20年前那会儿还没有很多人在做这个。20年前，国内有些学者在做再生混凝土因为08年发生汶川地震之后，四川那边很多房子倒了，很多这种混凝土重新利用，所以很多从灾区挖了很多这种再生混凝土重新利用。但是回过头来，大家来看，10年20年过去了，再生混凝土实际上在我们土木领域已经有了大量的使用，包括很多非常有名的学者在做。那么在几年前呢，我在英国留学的时候，他们开始做什么呢？比如说我们既有的建筑结构物的梁子，他们直接从现场拉回去，直接用。比如说我们现在这个楼可能是用了大概50年、100年，用完之后，它的这个梁跟柱直接拆下来，注意是混凝土梁柱，直接拆下来，直接用到，就跟比如说你的关节坏了，对吧？就跟人做器官移植一样，他们是这样子的。大家知道这种欧洲还有城市化，在100年前就完成了，很多这种基础建筑用了50年、100年，他们没有把它砸掉，像我们是把它砸成，他们是直接梁是梁柱，我们还直接用。所以呢，今天这个Cucuzza他的这个 topic 呢，就是我把这个钢结构这个想法非常大，我也是第一次听到这样的，相信你们应该没有听过这样的 topic 吧？我也是第一次听到，就是说这种钢结构不管是公子形钢还是各种各样的形钢，不管是结构形钢还是非结构形钢，就是从原有的建筑物中直接拿来我用到新建的这种建筑，或者说加入改造的。所以呢，我觉得这个 topic 非常的有意义非常的有趣，而且呢，这个应该是未来的一个发展趋势如果说从二碳排放的角度，从废物利用的角度，它一定是一个趋势。那么它在这方面呢做了大量的探索。那么大家有什么问题没有 ？Any questions? Any questions? OK， 那个刘金龙，那你来问，你做优化嘛？你来问一问吧，有什么问题？They are so shy, right? OK， 那个
You can speak in Chinese if you want.
Yeah， 你可以讲中文，如果你觉得英文不太好，我可以当你的翻译。
有的一个量的废物的一个程度嘛，对吧？我这样可以降低它的成本跟碳排放。但我看好像主要侧重是在那个固定部区，只是优化那个尺寸，就是好像没有把这个拓扑的比如说那个横架的那个拓扑构型给考虑进来。如果说可以把这个拓扑构型，包括它的尺寸，还有它前面形状，然后再加上那个切割之后的废物最小的这个目标的话，这样的问题是不是会更容易一些？对吧？
Okay. This question is like in your optimization, you just consider the size or shape of region. Do you need to consider like optimization size, optimization shape, and also the minimum waste from industry together, or combine some of the factors together in your optimization problems? Yeah. This is this question.
Thanks. Thanks for the question. Of course, I had just the possibility to I have just 40 minutes, so I try to condense all the information. But here, for example, here, in this case, take a look. A1, A2, A3, A4 are cross section. So in this optimization, for example, I work simultaneously on size, shape, and topology. For example, the size of the elements will change dynamically during all the optimization. They change the age of this dome, that is shape, and the topology, in this case, it was not taken into account. This is the real challenge. We have to take into account topology optimization in the new steps. But this is why I'm working with Professor Kangao, because I need to share some information about this, because topology optimization is quite challenging, you know. It is computationally expensive, and in the literature, we know very well that there non-exist algorithms that perform well in size, shape, and topology. We have algorithms that perform well in size, shapes, algorithms that are good for topology. The problem is that we want size, shape, and topology are the same. Probably what we will develop is, at first, we will, for a designer that's going sub 2000, the first step is topology optimization. Then, after this step is defined, is established, we can use the results of the topology optimization in order to perform on this outcome, on this output, we can perform size and shape. So in the future, we will implement a tool that is a multi-stage optimization level. Topology, that's sketch the draft, the main idea of the building, and then we will work on size and shape of the structural elements.
Professor, do you have any questions? No? Any other questions? 有问题吗？ No? Any other questions? 我们有问题，他们都太害羞了，不敢。中国学生就是有这样的问题，就是经常。大家有什么问题吗？ So I'm not sure. Can you see it online? There are some people online.
Yeah, I already asked, but nobody answered me. So no. However, I will share the presentation, and if you have some doubts, you can contact me at this email. Professor Kangao knows this mail. My mail is this one. You can contact me, so don't worry about that.
Okay. Thank you very much.
Thanks you too.
Let's take a picture. Yeah. Cheers.
Take a picture with this. Like this.
Energetic. Yeah, we put something on paper.
Yeah, of course.
Yeah, I think whatever you say, maybe you can put some overview or review paper or what.
Yeah.
I will participate in the conference, so.
In Japan, I don't have time.
Okay, so maybe